Hello. In this video lecture, I will be covering Chapter 10, Module 10. The topic is called Dynamics of Rotational Motion. Last time we covered rotational motion. Specifically, we studied the kinematics of rotational motion, where we concentrated on studying the angular velocity, angular acceleration, and angular displacement. For example, we gave the example of a bicycle wheel that is initially at rest and then it goes into motion. Say you have a initial angular velocity omega naught with some initial angular acceleration. What is the initial velocity after some time t, and so on. In this chapter we will be concentrating on the dynamics of rotational motion. What that means, if you remember, dynamics means what are the forces involved that is causing the rotational motion, and we refer to those kind of forces as the torque. So that's basically the subject of this chapter. There are two major topics here in this chapter: the concept of torque and angular momentum, which is analogous to linear momentum that you have studied when we covered collisions. So those are the two major topics here. So let's start. So we begin with the study of torque. T-O-R-Q-U-E. The torque has the symbol in our book, the Greek letter tau, and this torque is equal to the moment arm R times F. This is in the scalar form. For those of you who are familiar with vectors, the torque is equal to R cross F, where R, the cross here is the cross product. But anyway, this is not in our book. So what is RF? R here is called the moment arm. And it is basically a distance, but I'll come back to it in a sec. And of course, F here is the force. Okay. To give you an example, imagine you have a wrench that you want to use to loosen a bolt. So let me draw a wrench. I'll try my best to draw it. Something like that. Just a little bit thin, but that's all right. And let's assume that there is a stubborn bolt in here. Here it is. This is the bolt. Try to make it hexagonal in shape like that. That's the center of the bolt right here. And let's assume that you are applying a force on it like that to loosen it. Okay. I'm going to call this force F1 for now. Okay. Now, if we assume that the center of the bolt is right at that dot, or you can think of it like there is an axis of rotation right at the center right here. So the distance from the force of application, this force, basically this is where my hand is, right? My arm. And so I am pulling on it or rotating it in this direction right there. You see what I'm saying? And let's assume that the distance from this force of application to the axis or the center of the bolt, somewhere right here, okay, I'm going to call it R1. This R1 is what we refer to as the moment arm. Got it? And the key here is this, is that the moment arm R1 must be perpendicular to the force. This is very important. If it is not perpendicular, you want to take only the perpendicular component. Okay, we'll do a lot of examples on that. But this is the first thing that you need to know, is that it's a must that R is perpendicular to the force. Okay? In order for the torque to happen. In order for the torque, tau, to happen, is that the moment arm has to be perpendicular to the force. I'll give you another example. Let's say you want to open up the door of, say, the bathroom in your home. okay? And this is a top view. So here is the door. Again, we have a top view here. Here is the bathroom door. Let's assume it is closed now, like that. And this is the hinge. Let's put the hinge, let's put it here. Here is the hinge, all right? And here is the knob. Okay? And let's assume that you want to open it in this direction. Okay? So what you do is that you hold the knob with your hand and then you push on it. You see what I'm saying? And what will happen, the door is going to swing like that. It's not a good arc, but you get the idea, I hope. Here is the door right here. Hold on, let me get it better. So it's swinging like that. You see what I'm saying? So as you can see here, this is right here is the axis of rotation, and this is the applied force. And where is the moment arm? Again, the moment arm is the distance between the force and the axis of rotation, which is right here. Remember, the door is swinging about the hinge, which is where the axis of rotation is. So basically, the moment arm is basically where the force is located times all the way to the hinge right there. So in this case, the torque that you have applied, tau, is equal to Rf. Okay, later on we're going to do some numbers, but that's basically what it is. You got it? Okay, one more example. Let's say that you park your car at an inclined plane, and for just in case you don't want the car to roll back, you pull on the handbrake. Okay, so the handbrake, let's assume the handbrake on your car is on the floor, okay, right at between the passenger seat and your seat, the driver's seat, right there in the middle. So let's say that you pull on it, and let's look at, so let me draw a handbrake. So it looks something like that. Here is the floor right here, and here is the handbrake right there. Let's say it looks something like that. And then let's say that you are pulling on it, and let's assume that you pull on it with the force that looks like that. Here is the force that you, with your hand, right? And let's say the force is like that. Here is the force that you applied, F, okay? Now, assume that the handle here, a bit underneath that, it basically is rotating about this point right here, right? So notice here that the distance, the moment arm between the axis of rotation, the dot right there, and the force, call it R, as you can see here, it is not, R is not perpendicular to F. That's what I'm trying to say, right? So suppose that the angle here is equal to phi. Okay? So what does that mean? Well, we said that the torque, in order for torque to happen, that the force that is causing the torque must be perpendicular to the moment arm. In other words, this force, let me use a different color. This force has two components. One component like that, right? And the other component is like that. Okay? This component, your book calls it the radial component because it's in the direction of the radius. You see that when the handbrake moves, it makes an arc, if you will, right? That arc, so you can think of this R, the moment arm, is a radius. So he calls it the radial component. Obviously, this radial component cannot move the handle either up or down. The one that actually move it is this component, and we call it the tangential component, F sub t, because this is change it. Here is the motion of the door handle. Excuse me, not the door handle. I'm sorry, the handbrake. Right there. It's not very good. Like that. So, in other words, the one that is causing the torque is F sub t, not F sub radial. You got it? So in this case, the torque is going to be equal to this. The torque in this case, tau, is equal to R F sub t. the tangential component of the force. Well, what is the tangential component of the force is equal to? If you look at the diagram, the tangential component is basically F sine phi. See that? So therefore, the torque in this case is RF sine phi, assuming that we know what phi is. You see what I'm saying? And of course, assuming that we know what this force is. This F, we know what it is. What's the value of it? So in this case, the torque is actually just the component, the tangential component of that. Okay? All right, good. Now, one more thing. I can also, let's assume, suppose that, again, let me just say the color. Suppose that you don't know the angle phi, but you know the angle here. Let's say this angle. Let's call it theta. Okay? In this case, F sub t is equal to what? It's equal to F cosine theta. And therefore, the torque in this case, you can either use this formula right here or RF cosine theta. Either or, it doesn't really matter, you'll get the same answer. You see what I'm saying? Both are the same, but you make sure that you understand your trigonometry. Is it a sine or a cosine? Now, your book by default, he just puts sine there always. But that sine, you want to be careful where the angle is located, okay? All right, good. Let me start with an example, example 10.1 from the book. Trying to find it. There it is on page 284. Let me go to the book. It's right here. 284. And it is... okay, we need to read this paragraph first. There we go. He says in our first example, we will see that how we can use a lever arm to greatly increase the torque without having to provide more force. Suppose, for instance, that an amateur plumber, unable to loosen a pipe fitting, slips a piece of scrap pipe over the handle of his wrench. He then applies his full weight of 900 Newton to the end of a cheater by standing on it. The distance from the center of the fitting to the point where the weight acts is 0.8 meter. I believe this would be the moment arm. And the wrench handle and cheater make an angle of 19 degrees with a horizontal. Find the magnitude and direction of the torque of his weight about the center of the pipe fitting, blah, blah, blah. Okay, let's look at the picture. A picture is always better than 1,000 words. There we go. There's the picture. So here is the foot of the plumber. Here is the big wrench. Here is the stubborn bolt right here. So what he's doing, he's pushing. Okay, he's pushing with a force of 900 Newton, which is basically his weight, he said. And then the moment arm, which is from the point of application, which is the force, all the way to the axis of rotation. Remember, it's going to rotate like that. You see what I'm saying? It's going to make a circle like that. And that circle, what's the direction of that circle, guys? That would be like this, correct? That would be what? Imagine this force, this red vector would rotate about this point. It's going to go like that. Is that clockwise or counterclockwise? That's counterclockwise. So if it's counterclockwise, that will be the direction of the torque. Got it? Okay. And that's the moment arm. And this is the angle 19 degrees right here. Okay? So I need to find, as you can see here, the moment arm is not perpendicular to the force. So I need only to get the component of the force that is this way, the tangential, not the radial. Got it? Okay, so those are just quick thoughts before we get into it. Here it is right here, actually. You have a diagram of it right here. But anyway, let's do it our own. So what I have in here, oops, I want the black color. Okay, so what I have the following picture. Let me draw the picture. So here is the wrench. I don't need to draw a wrench. This is just the moment arm right here. This is the the bolt or whatever it is, and then he's pushing on it directly downward like that. I'm trying to make it downward with my hand. There we go, 900 Newton. Let's call it F, okay? And this is this angle right here, he said it's 19 degrees, okay? So if this angle 19, that means this angle is also 19. Make sense? You can pause the video and think about it. So the component that I want really is this one. This is the component. This is what I call, your book calls it F sub t, okay? There we go, that's better, okay? And he said the moment arm, R, is equal to 0.8 meters, okay? And I want to find the torque. Well, the torque is equal to RF, okay? And F here is F sub t. It's always F sub t. And look at how F sub t is related to F. As you can see here, it is RF cosine 90 degrees. Make sense? Not sine. It just depends on the geometry of the problem that you're dealing with. And that's basically what it is. So we just plug it in. So we have 0.8 times 900 times cosine 19. Make sure that your calculator is set in degrees, not radian, otherwise you'll mess up your answer. And if I do this, trying to find my calculator, so it's going to be cosine 19 times 900 times 0.8, answer 680.8. I got this, so you have a 680.8 for the torque. You got that, guys? Now, what is the unit of torque? I forgot to mention that. So we said that torque is RF. I like to write it as RF, not FR. And of course, the R here is meter. The force is Newton, so it's Newton meter. Okay? Your book uses Newton meter. I like to use meter Newton, but it doesn't really matter. So anyway, so we have a Newton meter like that. Okay? Now, what is the direction? This is basically the magnitude of the torque. Okay? What is the direction of the torque? Now, remember, the direction of the torque is always either clockwise or counterclockwise. That's it. There's nothing in between. Unlike force, it could be right, left, up, down, whatever. But the torque, because it's a rotational dynamic, so basically it's going either clockwise or counterclockwise. So let's look at that. Looking at this diagram right here, again, imagine this F sub t. The best way to think about it, imagine this F sub t would start orbiting, quote unquote, about this point. If it start orbit, it's going to go like that. See that? See, if the point is here, let's say the point is right there, assume. Well, it's going to start orbiting this way, which is clockwise. But no, it's going this way, and that's a counterclockwise. So that's CCW. That's the direction. Okay, this is called the direction here. And that's the magnitude, of course. Okay? All right, good. One more. I'm looking at my notes here. Oh yeah, this one is a good one. Example. Oh, this is just for my notes. Okay. Here's another one. It's also go back to the door, the bathroom door. So let's do this example. So we have a bathroom door. And let me draw a top view of it. I'm just going to match my notes. It looks a little bit different from the one I did just a minute ago. Here is the door. Remember, it's a top view, guys, right? Here is the hinge right here. And here is the doorknob. There we go. And so we have this is a top view. So the question is, find the torque produced by 300 Newton force applied at an angle of 60 degrees to the door. Okay, I'll show you what that means. Okay, so the force is like that. There it is. This force is equal to 300 Newton, and the angle, again, it depends. Is the angle here or here? And that's why it depends. Is it a cosine or sine? So the one given to us is this one. Okay, and the what else given to us? Oh, okay, and the moment arm, he said that the length of the door from the hinge to the knob is 2 meters. Got it? Okay. So how do we do it? Okay, you can pause the video and try to do it yourself, but basically what we do, let me change the color. If you have a problem with red, if you have a, let's say you're colorblind to red, please let me know. I always use red. Okay, so the one that is causing the torque, remember the moment arm is this one. This is the moment arm, R. So the force is going to be perpendicular to us. It's basically that, my F sub t, if you will, right? So that means this force is the component of this force here, and that will be sine, correct? So F sub t in this case is F sine 60 degrees. You see what I'm saying? Now, if the angle 60 is given here, will be F cosine. It all depends where the angle is, which angle is given to you. So you need to know that. All right, that's it. We are basically done with the problem in this case. I mean, the problem is not really that hard once you know the component. So tau in this case is RF sine 60. Plug in everything, so you get 2 times the force is 300 times sine 60, which is 0.866, and then you just plug in everything in there, and you will get 520. I'm just copying it for my notes. Meter Newton, and there we go. Okay. Okay, good. The next topic about torque, there are 2 more subtopics regarding torque before we jump into angular momentum. And I'm going to talk about equilibrium. You remember this word, equilibrium? We've covered it in I forgot what chapter, chapter 4, I think, 3 and 4. Okay, we said that equilibrium means what? All the forces on an object sum up to 0. The statement of equilibrium basically sigma f as a vector equals 0. Okay, which basically, and if you resolve this vector into 2 components, becomes sigma f sub x equals 0, sigma f sub y equals 0, and we said this is the condition for equilibrium. Well, there is an additional condition. And that additional condition is that the sum of the torque on an object is also equal to 0. Okay, so in other words, we have 2 conditions for equilibrium. Okay, the sigma f equals 0 and sigma tau equals 0. They both are necessary condition for equilibrium. We just didn't talk about it last time, but that's an important condition that we have to take into consideration. Okay, let me give you an example. I'm going to do the ladder problem, which a lot of students find difficult. But let me start with a simple example. Yeah, let's do this one. Again, this is for my notes, I believe. Yes, it is. Okay, and I call it a seesaw example. Imagine 2 children in the playground. Seesaw. I'm sure all of us have played with the seesaw. So you have two children in a playground or playing on a seesaw, okay? Let's assume that the two children are just sitting on the seesaw, but they're not moving, okay? Before they start moving, they're just sitting there. One child has different mass than the other child. So let's draw the seesaw first, and then I'll tell you what we want to do. So here is the seesaw. It's basically a plank, a wooden plank. Here it is. And right in the middle, right here, you have the fulcrum, or where it's balanced right there, you know, something like that. And then you have the one child, let's say, sitting right, so let's make him into a stick child. If I can draw a child, there we go. There we go. Smile. Let's make a bigger face. There we go. There we go. Okay. And his sister, there she is. Bear with me. Oh, gotta give her hair, right? There we go. Oh, her arms. There we go. All right, so let's assume the sister is 350 Newton, okay? That's her weight, 350 Newton. And the boy is 500 Newton, okay? Remember Newton here, it's not pound, which means how many kilograms is that? Divided by 10. So that's, she is 35 kilogram. How many pounds? Basically multiply the kilogram by 2 and you'll get the pound. So she's about 70 pounds. You see that? So if you give in Newton, divide by 10, you get kilogram. Multiply the kilogram by 2, you get pound. I mean, this is just mental math. It's not accurate, but it'll give you a good approximation. If you want to have a feel for this number, 350. Well, what is that? Is that a large number? Is she too massive or no? Well, Newton divided by 10, you get kilogram. Multiply the kilogram by 2, you get pound. Got it? Okay. So the boy, if he's 500 Newton, that makes him 50 kilogram. What? 100 pounds. Got it? Okay. All right, continuing on. And let's assume that the boy is the brother. He is 1.5 meters from the fulcrum. Okay? The fulcrum is basically right here. So you can imagine that everything is balanced about this point right here, guys, right? So you can think of it like an axis of rotation. This axis, as you look at it, is actually going through and between your eyes, okay? So it's going in and out, this axis of rotation, okay? And that axis, so the two children are going up and down about the axis of rotation. Instead of saying, in other words, if you look at the motion of the seesaw on this side, it's going to make an arc like that, and it's going to make an arc like that. You get the idea? Okay, I hope you are visualizing all that. This is important to visualize. All right, so, and then we don't know, or let's just say, now, since the sister is lighter than her brother, we're going to ask the question, how far the sister should sit on the seesaw in order for her to balance exactly with her brother. You get that? See, if she sits right here, she's not going to balance very well with her brother. Her brother is going to be outweigh her. If she sits way out, let's say that the seesaw extends far away, she may, outweigh the brother, and the brother will go up. So where is the magic number? Where is that right distance that in order for her, when she sits at that distance, she will balance with her brother? You got the idea? So we're going to call that X. I don't know what it is. We're going to find out using the law of equilibrium. Sigma tau equals 0. Okay? So that's basically the situation that we have. Here, let me just, I'm looking for the statement to write it down just for the records. So it says here, determine where the 350 Newton child, I'm copying this from my notes, should sit to balance the system. Well, all right, the system. Got it? Okay, so how do we do it? Well, first of all, I'm going to redraw that. I'm going to redraw the seesaw without the siblings. So here is the seesaw, but I'm going to put the forces in there, free body diagram. Here is the seesaw right here. Here is the fulcrum. And here is the sister, 350 force. I'm going to call that F1, shall we say. And she is an X away from the fulcrum right here. And then the brother is 500. Let's call it F2. And he is 1.5 meters away from the fulcrum. Got it? Okay, so how do we do it? Okay, here is how we do it. Let me apply the equilibrium position. Remember, there are three equations for equilibrium. Sigma Fx equals 0, sigma Fy equals 0, sigma tau equals 0. Got it? These are the equilibrium position formulas, okay? Now, you agree with me, sigma Fx does not apply for our condition. Okay, why doesn't it apply? It does not apply because there is no X component here, right? It's all in the Y direction. So we can just ignore that. Sigma Fy equals 0. Well, let's collect them. What do we have here? Well, we have, how many forces do we have here? 2? No, we have 3, right? We have 3. The third one is basically the reaction right there, right? Action, reaction. Just like you're sitting on the chair, there's the normal force. So that is a normal force right there. Don't forget that. Okay? So in this case, it's going to be N minus 500 minus 350 equals 0. So the normal force, assuming that, and by the way, we are assuming that the seesaw, the balance itself, is weightless. Okay? We're just going to assume that, which is not realistic, but let's just assume that. So in this case, it's going to be, what is that? 500 plus 350, that would be 850, correct? So that's 850 Newton. There we go. That's the normal. Okay. It's not going to give us much help. This formula is not going to help us much, but that's basically how you find it. All right. Now the next step, I want to use sigma tau equals 0 to find that distance. Okay. How do we do it? Here's how you do it. Watch and learn. What you want to do is you want to pick a point on the system. It doesn't really matter which point, but pick a point on the system, and you want to take the torque about it. In other words, you want to assume everything goes around it. Well, the most logical point to take is right at the center, where the fulcrum is, right here. So I'm going to call this point right here. I'll put it in red, just to emphasize it. So I'm going to call this point right, come on, there it is. I'm going to call it point O. All right, so this is O. Okay, so in this case, I want to do sigma tau about O equals 0. Do you see my notation? So this O here is not a knot. It is this. You are taking the torque about O. I could have called it A. So in this case, sigma tau about A, sub A equals 0. You got that? But I like to call it O. What does that mean? Well, here is the meaning of it. Before I do anything, there is a convention in our book and in physics in general. Clockwise is negative. Counterclockwise is positive. Okay, make sure you write it down somewhere. This is very important. Just like you say, X and Y axis, the positive X axis, negative X axis, the negative is to the left, the positive to the right. Then the Y axis, the upper one is positive and the lower one is negative. Well, clockwise is negative, counterclockwise is positive. Okay, make sure you understand that. Memorize it. Write it down somewhere. Okay, why do I emphasize that? Well, because when we calculate torque, we need to have a sign convention, and this is our sign convention. This is very, very important. Okay. Okay. So we did two things so far. I picked a point, which is basically the fulcrum, and I called it O. You may not know why, but it's okay. Be patient. The second thing, we created a sign convention. Clockwise is negative, counterclockwise is positive. Okay. Now here is what I'm going to do. Watch. Let's go to the diagram. Let's start with the 350 Newton right here. The vector is pointing downward, right? Now imagine if it is again orbiting about O. It's going to go like this. Watch. Yes? Imagine 500 orbiting about O. It's going to go like this. Make sense? Well, look at let's go back to the 350. When it orbits, okay, about O, is this clockwise or counterclockwise? That's clockwise. That's negative. However, look at this 500. 500 is going like that. Is this clockwise or counterclockwise? That's counterclockwise. That's positive. Now I come back to this, sigma tau equals 0. And remember, tau is equal to what? Let me just remind you. Tau is equal to RF, correct? I don't need the sine or cosine because everything is perpendicular. Look at that. The force here is perpendicular to the moment arm. Force perpendicular to the moment arm. I don't need to bother with the sine and cosine here. Cool. Let's start with the brother, F2, 500. So it is, we said that this is counterclockwise. So it's going to be plus RF, right? It's RF. What's R? How far is it from the fulcrum? 1.5. Times F, F2. I'll come back to it. Done. This is as far as the brother is concerned. Let's go to the sister. The sister is going like that, her force. This is counterclockwise. Clockwise. Negative. And what's the distance? How far is she from the fulcrum? X, that's what I'm looking for. Times what? Her weight, or the force, 350. Oops, I'm sorry, let me just make it F1 for now. Just like that. Equal what? Equal 0. There we go. I'm done with the torque equation. Now plug it in and find X. So now I have 1.5 times 500 minus X times 350 equals 0. All you need to do now is just to solve for X. So in this case, X is equal to 1.5 times 500 over 350. And I would use my calculator to do that. And when I do it, I got 2.14. There we go. See how it's done? In other words, go back to the diagram. In order for the brother and sister to balance on the seesaw, he has to be, if he is 1.5 meter away from the fulcrum, she must be, I forgot the number, 2.14 from the fulcrum, somewhere here, for example, okay, in order for both of them to balance each other, and not either of them or neither of them will tip the other. You get that? Okay. That's the meaning of it. But make sure you understand the sign convention, and you always take the torque about a point. You must determine the point, always, okay? All right, good. Let's do a tougher problem. And that's the ladder problem, and that's an example 1012. It is a difficult problem. I think it is. And by the way, I'm doing equilibrium before I did, I'm skipping a section, but I'm going to come back to it later in the video. I'm skipping for now torque and angular acceleration. I'm going to do that at the end of the video. So I jump to equilibrium, which is section, flipping the pages, sorry. Oh, section 10.6, okay? All right, so I want to do example 1012, and that's page 304. Let's go to it. Here it is right here, 10, 12. So what you have in here, a ladder leaning on a wall, as you can see, and then you have a guy standing here painting the wall or whatever he's doing, okay? So he calls the example climbing a medieval ladder. Usually the example is usually a painter on a ladder. But anyway, okay, it says in this example we will consider the classic static equilibrium situation of a ladder leaning against a wall. Suppose a medieval knight is climbing a uniform ladder that is 5 meters long, so that's the length of the ladder, and heights of 180 weight, excuse me, and weighs 180 newtons. So you get the guy is 180 newton. Well, how many kilograms? Divided by 10. Oh, that would be the ladder then. Yeah, that'll be divided by 10. That'll be 18 kilograms. That's the weight of the ladder. And then how many pounds is that? Just multiply by 2, right? 36. And so on. Okay. The knight who weighs 800 newton, which is how many kilograms? Roughly 80 or 160 pounds. Stops a third of the way up. Okay, so this is the last. So a third of the way up the ladder. The bottom of the ladder rests on a horizontal stone ledge and leans across the castle's moat, I don't know what that means, in equilibrium against the vertical wall that is frictionless because of a thick layer of moss. Goody. Okay. The ladder makes an angle of 53 degrees. That's basically what counts. Okay, so we have a 53 degree here, okay, with the horizontal, conveniently forming 3, 4, 5 right triangle. Okay. A, B, and C. Find the normal and friction forces on the ladder. Find the find the minimum coefficient of static friction between the needed to prevent the slipping, and find the magnitude and direction of the contact force on the ladder. All right. Okay. So let's do this problem. I'm going to call it the ladder problem. 10, 12. It's a classic problem you find in just about every physics book. For those who have taken physics, probably have seen it before. Anyway, so what we have, here is the picture. Here's the wall. Here's the floor. And here's the ladder right there. Just like that. And you get the guy standing 1/3 of the way from down, 2/3 of the way from the up, right? So here is, there we go. Big ears, how about that? All right, and so let's write down the data. So we have a ladder. The length of the ladder is 5 meters. The weight at the center of mass of the ladder. Here is the center of mass of the ladder, right? Okay, I'm going to call it W sub circle with an X. That's the center of mass of the ladder. Is 180 Newton. All right. The weight of the guy, the painter. Let me call him painter. How about that? He's 800 Newton. And then he stops 1/3 of the way up the ladder. Okay, so he's 1/3 of the way up the ladder. And before I ask the questions, let's look at what are the forces on the ladder. Well, let's see. I mean, here is the weight of the guy. Let me just put it right here. That's the weight right here. So basically we have the weight of the ladder itself. I'm going to call it W sub X like that. And then you get the weight of the painter like this. You see what I'm saying? And then what else? What other forces? Well, since the ladder is pressing against the wall here, so there should be a normal force going like that. Okay? Make sense? And that force, I'm going to call it N sub 1. I don't know what your book calls it. Yeah, he calls it N sub 1 actually. Okay. And then again, also the ladder is pressing against the wall, the floor right here, so that will be another force going up like that. I'm going to call it N sub 2. So two normal forces. They're not necessarily equal. They could be, but they're not necessarily equal. I don't know if they're equal or not. What else? Well, what's preventing the ladder from slipping? Well, you get the friction force. If there was no friction, it will slip. You see what I'm saying? So there is a friction force going this way. And then you get the angle here, 53. Got it? So those are the forces that we have. Okay? Now, he said the length of the ladder is 5. And he said the whole formation is a 3, 4, 5 triangle. So that makes it, this is a 4 meter right here. That's just given to us, which is nice. And this is 3 meters. Okay, and the hypotenuse, of course, which is the length of the ladder, is 5. So 3, 4, 5. Okay? All right. He's asking for, he wants to know, A and B and C. A, he wants what is N sub 2, the normal, and what is the friction force. Okay? B, what is the coefficient of static friction needed to prevent it from slipping? To prevent from slipping. And then C, what is the force R? I'll come back to it. You say, what is R? I'll come back to it, I promise. I don't want to clutter the drawing. The R is there somewhere. I'm going to show you what it is at the end. Okay? So that's base. So let's find N2 and the force F first. Now, before we do anything, always apply, since the whole system is not moving, that means the system is in equilibrium, correct? And if it is in equilibrium, then we can apply the 3 laws. Sigma fx equals 0, sigma fy equals 0, and sigma tau equals 0. Okay? Those are the 3 forces that we're going to apply, the 3 formulas that we're going to apply, and hopefully we will be able to solve this problem. This is a tough problem. It's actually the toughest problem in the chapter. So I hope you're paying attention to it. So let's start with the good news about this problem is there are no angles, as you can see. They're all either in the x direction or in the y direction, which is nice. So let's start with sigma f sub x equals 0. What do we have here? Look at it. Look at the drawing. Sigma fx is going to be minus n1 plus f equals 0. That's it. Okay? I'm going to box this equation. I'll come back to it in a minute. Equation 1. Sigma fy equals 0. We got a bunch of them. We have N2, we got W and WX. See that? The weight of the ladder, the weight of the painter, and then they get the normal. Got it? So that's going to be N2 minus the weight of the painter minus the weight of the ladder equals 0. Okay? Box it. I'll come back to it. I'm going to call it equation 2. And the third one, which is the toughest. How do I make this not disappear? I want the drawing. Can you please pause the video and then draw that on a piece of paper? Because I want to be taking the torque and looking at this equation. See what I'm saying? Okay. So now, you know what? I'm going to draw it again. Here we go. Let's do it very quickly. It's not going to look as pretty as the other one, but that's all right. There it is. Okay, so we have here N2 F N1 and then right in the middle W X, and then right here, let's say, is the guy, the painter, like that, right? Okay. There he is. Okay, there we go. Before I do the torque, I want to show you something else here. Let me change the color. Remember, torque, what's associated with torque is a force and a moment arm, right? And the problem is that the moment arm have to be perpendicular to the force. As you can see here, the ladder, okay, the ladder is inclined, has an angle 53 degrees here, right? And so how are we going to do that? So every one of them, every force here, there's an angle here, there's an angle here. But there is a trick to it. And that's what I'm going to show you. That's why I have to draw it again. What you do is you ask the question, remember, well, okay. Sorry. What I want to do, I want to take the torque about this point right here. You can take the torque about this point if you want to. But I want to take it about this point. I'll tell you in a minute why. But I want to take the torque about this point. So I'm going to call this point O, the big O. In other words, I'm going to do sigma tau about O equals 0. And this O right there is this one right here. Got it? Okay. Now, next. We know that this distance is 4 meters, right? 3, 4, 5 triangle. And this one is right here is 3. Sorry, it doesn't, it's not drawn to scale. But anyway, there we go. Okay? Here's what I want to do. I want to know this length right here. And I want to know this length right here, in red. Why? I'll tell you in a second. What is this length? If I tell you that this whole thing is 5, okay? And this is the center of mass, which means this distance is what? 2.5. You agree with me on that? That's 2.5. So what is this distance from here to here? Well, any idea? Well, this angle is 53, correct? And when you do the math, you'll get this distance to be, the moment arm is 1.5 here. You can pause the video and calculate it, but I'm just going to write down the calculations here. And this one, it turned out to be 2 meters. Why 2 meters? Well, he is 1/3 of the way, so that's 1/3 of 5. So I'm saying, remember, the full length is 5. So here's 1/3 of 5, and this angle is 53. And you can sit down, you can do the calculation, you'll end up with that. This length right here is 2. Notice something. This is the moment arm, if I'm taking the torque about O, that's the moment arm. And look at the moment arm, it's perpendicular to W. This moment arm is perpendicular to W here as well. You see what I'm saying? And this moment arm is perpendicular to N2. It's not perpendicular to F, so F does not produce any torque. That's the trick. So now when I take the torque about O, this equation right here, it's going to look something like that. Sigma tau about O equals 0. I'm going to have, again, keep in mind, clockwise, negative, counterclockwise, positive. So let's start. Let's start with Wx, sorry. Okay? Wx is going to go about the point O. Look at that. That's what? That's a counterclockwise. It's going to be plus W sub x times 1.5 plus, same thing with W here. This W right here is going to go about O. See that? Counterclockwise. So it's going to be plus W times, how far is it? 2. And then plus, look at the friction. Look at the friction, okay? Say this friction force right here. If I put it right here, see the distance from here, from the friction, all the way to O is 4. So it does make a torque. See that? And that is counterclockwise. So it's going to be plus F, or 4, times F. Minus, what about N2? Look at N2. N2, and here is the moment arm for O. So that's going to be N2. But look at that. N2, if you go make it go around O, it's going to be clockwise. See that? It's clockwise. So that's going to be minus 3 times N2. Close it. And there we go. We got the torque equation. If you can do this by itself, you're basically done with the problem, with this problem. The rest is just easy, really. Now all you need to do is you go back to the force equation 1 and 2 here and try to get what whatever you can out of them to plug it back in there. How do I do it? Well, let's see. He says, I know what WX and W are, right? He said what they are. He said, go back to the beginning of the problem, WX is 180 and W is 800. Okay? I got a lot of data here, so I can just plug them in. So in this case, WX, that's going to be 180 times 1.5 plus 800 times 2 plus 4F, I still don't know what F is, minus 3N2 equals 0. Work it out, you're going to end up with 270 plus 1,600 plus 4F minus 3N2 equals 0. And then I end up with 1870 plus 4F minus 3N2 equals 0. And I'm going to box this equation. I'm going to come back to it. I'm not done yet. And I'm going to call it equation star. How about that? Okay? Now let's go back to equation 1. Here it is. I hope you're taking notes with me. Here's equation 1. Here's equation 2. Okay, I'm not going to go back to them. I assume that you have them on your piece of paper there. So equation 1 says F equals N1. And equation 2 says that N2 is equal to W plus WX, and that will be 800 plus 180, and that's 980. There we go. So now I know 980 Newton. So therefore, I know that N2 is 980 Newton. Okay? And if I go back to star and plug in N2 here, I can find F. Isn't that nice? So back to star. So I have 1870 plus 4F minus 3 times 980 equals 0. And then you can just work it out. F will be equal to 267.5 Newton. There we go. Okay, let me go back to what he's asking. Part A, find N2 and F. We already found them. We just found them. Now find the coefficient of static friction that is needed to prevent it from slipping. All right, well, we know that. F is equal to what? That's part B right here. F is equal to mu n. Which n? Which n, you guys? It's N2. The one right beside it, right here. This one. This N2 is directly related to F. See what I'm saying? Not this n. Think about it. You can make this as rough as you want. It's not going to affect the force here. See what I'm saying? It is N2 that is affecting it. All right. So in this case, we would have, therefore, mu sub s, that is equal to F over N2. And I got both of them. Here they are right here. N2 and F. So that's going to be 980. Oops, sorry. I want it. F is 267.5 divided by 980, and therefore mu sub s is equal to, calculate that, 0.27. There we go. This is the coefficient of static friction. Okay? And what else do we have here? So there we go. This is the last part. Now the second part. Now the last part, let me go back to the book and read it. Find the magnitude and direction of the contact force on the ladder at the base. Okay? Here is what that means. So you get this guy standing on the ladder. So you get all these forces on it. You get the weight of the guy, the weight of the ladder, You got the normal force from the wall pushing this way, you get the friction force going this way, and you get the normal force going up this way. What is the sum of all these forces? Well, the sum would be at the base. It will be some force, he's calling it F right here, at some unknown direction, some unknown angle, but it would be like that, okay? I like to call it R because R stands for resultant force. So I'm gonna, I go back to my second drawing. Oh, that's my second drawing right here. And let me make a different color, say green. This force is gonna look something like that. Some arbitrary direction R, and some angle, let's call it phi. Okay? So I want to find R and phi. Well, how do I find it? It's easy. Here is how you find it. Here's how you find it. R, this R is equal to, R sub x is the sum of the forces in the x direction, and R sub y is the sum of the forces in the y direction. Remember we did that in chapter 1 and 2, how to find the resultant vector? That's basically what he's asking for. So all you need to do is to find the sum of the x component and the sum of the y component. Well, what is the x component? Well, the x component are here, right there. Where did I find it? Oh, it's right here. There it is. This is the x component right here. You see what I'm saying? And the y component is right here. Or a better way of saying it is that since we're talking only about the base here, it's basically the y component would be n2 and the x component would be f. See what I'm saying? In other words, if I would draw that, let me take a different color. Purple. How about purple? So this green vector R comes from two component vector, f sub x and f sub y. And this f sub y is basically n2, and f sub x is basically the friction force. Okay? In other words, I don't need to do any calculations here. All I need to do is, that will be, R sub x here is going to be the friction force, and then the y here would be the N2. Well, the friction force is equal to what? We found it to be equal to, here it is, F is 267, and the normal force is 980, so that's going to be 267.5 Newton, and then this one is 980 Newton, and therefore R is the Pythagorean, and that will be 267.5 squared plus 980 squared, like that. And then when we calculate that, I need to calculate that, and 267 squared plus 980 squared under the root. Answer, I got 1020 Newton. There we go. That's the resultant vector. Okay? And then what is the direction of that thing? If you remember, tan inverse what? R sub y over R sub x. That's just a rule. So R sub y is in this case 980 divided by 267.5, and then therefore phi in this case will be equal to 75 degrees. In other words, this angle right here from the diagram, there we go, this angle phi right here is 75 degrees. Okay? All right. This is kind of a meaty problem, a little bit hard. I don't want to scare you. Don't expect a problem like this to be on the exam. It's just very time consuming. But it's important that you learn how to do it, and but do not expect it to be on the exam. A problem like it. Just very, very time consuming, and it's kind of tough. Okay, the next topic is torque and angular acceleration. I'm trying to find the section. Sorry. Torque and angular acceleration, section 10.2, basically the second section. I kind of skipped, came back. All right. Torque and angular acceleration. All right, this stuff is going to get a little bit simpler, I hope. Okay, what does that mean? Well, go back to Newtonian law, Newton's second law. We said that F equals ma, correct? Okay, so we said that if you have a force, and this force is exerted on an object with mass m, the object is going to accelerate with acceleration a, correct? Basically. Okay. Now, what if I have an object with mass m, same thing, but I am not exerting a force on it. I'm exerting a torque. Remember, torque is what? A torque is a force that causes the object to rotate. Just like you opening the door of the bathroom. It is a force, you're pulling it or pushing it. But what will happen, the door doesn't move forward, it's actually rotate about a certain axis. Okay, so that's what torque is. So what if I have a torque that is imposed or exerted on an object? Would it be an ma? It will be, what's analogous to it is this, that the torque is equal to, not ma, but I alpha. Isn't that interesting? Okay, so I here is the moment of inertia. We talked about it last time. Alpha is the angular acceleration. So this is basically F equals ma. This is in linear motion, okay, where tau equals I alpha in rotational fashion or rotational motion. Okay, this is so they're both analog of each other. This is the rotational analog, and this is the linear, rectilinear analog, if you will. Got it? Okay. The best way to explain it is through examples. Let me begin with one example from the book. I'm trying to find a very easy one before I go into a tougher one. Yeah, I'll take example 10.2. Let's go to it. That's on page 288. Okay, there we go. So what you have here, it looks like a wheel and somebody's pulling on it like that, or a pulley, whatever it is. He says figure 10.10 shows the same situation we analyzed in example 9.7. A cable is wrapped several times around a uniform solid cylinder with diameter 0.12 meters and a mass of 50 kilogram. Okay, this is the mass of the cylinder, this thing, this pulley, whatever you call it, that can rotate freely about its axis. All right. The cable is pulled by a force with magnitude 9 Newton, not much. Assuming that the cable unwinds without stretching or slipping, we will always assume that. Find the magnitude of this acceleration. Okay? All right. So basically what you have, before I do this problem, if we look at F equals ma, if we look at F equals ma, it will be something like, here's a box, here's the floor, here is a rope, and I am exerting a force, and the box, as a result of that, moves here, for example. Okay? And it's the mass of the box is m, and it's going to move with some acceleration a, and therefore F equals ma. Okay? That's the linear analog of it. Well, the rotational analog is what you just saw, okay? So that's basically the meaning of it. Okay, so we have example 10.2. So what I have in here, let me draw it. So you get this disc or cylinder, drum, there's a million names to it, and then it is situated like this. And then you have a force. And this force is equal to 9 Newton. He gives you the diameter of the drum or cylinder. Oops, not here, all the way there. 0.12 meters, and he gives you the mass of the drum is 50 kilogram, and he's asking, so here we have a cable wrapped around the cylinder. He said the force is 9 Newton. What is the acceleration, the linear acceleration that is? Okay, got it? Okay, how do we do it? All right, it's not bad. Basically, sigma tau equal I alpha. So sigma tau, or tau equals I alpha. Okay? We only have one force, so we just say tau equals I alpha. Tau here is RF equals I alpha. You follow me so far? I here is the moment of inertia for a cylinder, and the cylinder's moment of inertia is 1/2 mr squared times alpha, and then r is, what is r? R is nothing but from the point, the fulcrum, or the point of axis of rotation, which is right here, this dot right here, to the point of application, basically the radius. So r here is really the same thing as this big R. So it's just going to be big R F. See that? And F is given to us. So now I can just reduce things. This is cancel out. Remember, I'm solving for alpha. But before I do that, remember A equals R alpha. Remember that? Previous chapter? So I can plug it in there. So therefore, alpha is A over R. So plug it right there. So I'm going to have this equation becomes F equals to 1/2 mr times A over R. R cancel out again. And therefore, A, just do the algebra now, 2F over M. That's it. Make sense? Just plug it in. So I have here 2, F is 9 Newton divided by 50. So that's 18 over 50. And then when we calculate that, where's my calculator? There it is. I have 18 divided by 50, answer 0.36. So therefore, .36 meter per second squared. There we go. Simple problem, huh? Okay, very good. All right, let's do the next one. The next one is a little bit harder. Just a little bit harder. Example 10.3. All right, let's look at the book. There is a picture associated with it. No, there isn't. Okay, I'm going to draw the picture for you. He said dynamics of a bucket in a well. Okay, so let's go back to the old-fashioned well in example 9.8. In that example, we were limited to a conservation of energy analysis. I believe I did this problem in the video, but anyway. Now we want to use Newton's second law for rotation. What does that mean when you say that? Newton's second law, basically tau equal I alpha. Okay, this is just a fancy way of saying that. So Newton's second law for rotation, Newton's second law is F equals ma. Newton's second law for rotation is tau equals I alpha. Okay, and we want to find the acceleration of the bucket of mass m and the angular acceleration alpha of the winch cylinder. Okay, so let me draw the picture for you. So basically, you're using a well. You're using this pulley system to draw water from a well, and it looks something like that. Maybe I should go to the example. What do you think? Hold on. I believe there is a nice picture to it. Example 9.8, figure 10.11. Trying to find it very quickly. 9.8. Here it is. On page 269. Let me go back to it. Let me go back to it very quickly. 269. Just to show you the picture. Kind of a neat picture. Here it is right here. Okay, so you have a bucket, there is a well right here, okay, and there is a handle, a crank, and so you crank it up, and then the well comes up, and so we're going to draw this picture right here, okay. So this is the pulley, which is basically this stick that the cable wraps around it is this one, okay, and you get the bucket. Got it? Okay. Go back to page 288. There we go. There's no picture in here. But anyway, here is a picture. Here's how it looks like. So what we have is you get the drum. I'm going to call it a drum. He calls it a winch, whatever. And of radius big R. And then you got a cable, and it connects to the bucket. The bucket is right here. I'm going to turn it into a block of mass small m. The mass of the winch is big M. Radius of the winch is big R. And here's the water in the well. Okay. Now we're going to assume the height here is h all the way to this level of the water. I'm not sure if this is important or not. I don't think it is. I'm just copying it from the previous example. So what else do we have? So this is called a winch right here. Winch cylinder. Okay. This is the bucket right here. And so find A of mass M, small m, and alpha of the winch cylinder. Okay? That's the problem. All right. Please take notes, right? Draw this picture before I make it disappear. So how do we do it? All right, since we have two objects here, guys, we get the pulley or the winch, and we have the block. So I'm going to draw, each of them has its own forces. Each of them moves in a different way. The winch or the pulley rotates about its axis, where the bucket moves up and down. Okay, so each of them has its own dynamic. So I'm going to draw and get the equation of motion for each, and then see how they combine together. Okay, see the plan? So I'm going to start with the winch. Here's the winch right here. That's the radius, and that's O. Okay, the axis of rotation is O, and then you get the cable. Well, the cable is pulling or pushing on it downward like that. I'm trying to make it. Oh gosh, let me do it again. I'm trying to erase this thing, and then it just disappeared. Do it again. Okay, let's make it a little bit bigger. There we go. This is the tension coming from the bucket. You agree with me? I'm going to call it big T. And this is O, and that's the radius R. You got it? And the motion of the winch is this way. Got it? So now, I want to use Newton's second law of rotation, which is tau equals I alpha. What is tau here? Well, tau is RF. Big RT. Here is T, right? Remember, it's hung. This winch is held at the center, so that the weight doesn't mean anything. So the only force there is really is the weight from the bucket pulling it down like that. And then the torque is R alpha. Now make the torque go around it like that. This is right. If you make the torque, excuse me, the force T go around O like that, would that be what? Counterclockwise or clockwise? Counterclockwise. So that makes it positive. Got it? Now you can make a trick and draw the whole thing like that. And guess what? See that? It's going to be clockwise, going to be negative. You see what I'm saying? And you're going to end up getting the same answer anyway. So it really doesn't matter how you do it. But make sure you just your signs are consistent. Get that? So it depends on how you draw it. All right. Times, equals to I alpha. I here is the momentum of inertia of the winch. He said it's a cylinder, so that makes it 1/2 big M, big R squared times alpha. The R cancel out. And I end up with the tension T is equal to 1/2 big M R alpha. I'm going to box this equation. I'm going to come back to it in a minute when I work on the bucket. I'm going to call this equation 1. Got it? Okay, now let's work on the bucket. Here's the bucket. So what's going on with the bucket? Well, here is the tension. Remember, tension coming out of the body all the time. And here is the weight of the bucket, mg. It's moving in this direction. Right? So what do we got here? That's the direction of the acceleration. So the equation of motion here is going to be, remember, there is no rotation here, right? There is no rotation. It's all linear fashion. So it's just going to be sigma Fy equals ma, sigma F sub y equals ma. So in this case, I'm going to be T minus mg equals minus ma because it's moving down, correct? And there we go. We have equation 2. Now, somehow I need to combine those two together. Okay? How do I do that? Well, I'm not interested in the tension. He didn't ask me for it. So I can take this T equal 1/2 mr alpha, and I can plug it right in here. Got it? So let's do that. So plug 1 into 2. So that becomes 1/2 mr alpha equals mg minus ma. Okay, what I've done, I moved the mg here. It becomes a positive, right? Okay, but a equals to r alpha, which makes it alpha equals to a over r. I'm not interested in the alpha for now, even though he asked me for it. But I want to eliminate alpha for now. So I'm going to take this, and I'm going to take this alpha and plug it right here. So all this equation is going to be in terms of A, and then I'm going to solve for A, and I'm done with the problem. Got it? See the plan? So I'm going to do that. So this equation becomes 1/2 mr A over r equals to mg minus ma. R's cancel out. If I do the algebra, I'm not going to show it to you. If I do the algebra, you can work it out. You'll end up with A equals to mg divided by small m plus big M over 2. Just like that. Okay? Now, forgot what he is asking for. What else he asked for? Now you find the acceleration and the angular acceleration. Well, the angular acceleration is easy. If this is the acceleration, well, what's the angular acceleration? Well, A equals alpha r. So therefore, alpha equals to A over r. So all I need is to take this thing right here and divide it by r, and that will give it to me. You see what I'm saying? I think you can do that yourself. That's it. Okay? All right. Next topic. I have 2 more topics. This is a long chapter. Work and power. This is kind of a short section, but I'm going to go over it very quickly. Please take the time to read it in the book. That's on section 10.3. Okay, so what does that mean? Remember we talked about power, and we said power is equal to energy over time. Remember that? and we said, or it can be also written as work over time. And we said that work is F times X, remember that? Or because we're using rotational motion, I'm going to call it the arc length delta S. Okay? And then we know that from geometry, if I have a circle of radius r, angle theta, that's arc length. So arc length S is equal to r theta, correct? So in this case, this will be F r delta theta. That's for work. You see what I'm saying? But Fr is what? What is Fr here? Well, that's torque. So work is tau delta theta. And that's one famous equation for work when it comes to torque. Okay? Now we know that. Let's go back to the power formula. We know that power is equal to work over time, but work is tau delta theta over time, which is delta t. Well, what is delta theta over delta t? Go back to chapter 9. Delta theta over delta t, if you remember, it's omega. So therefore, power is omega tau, or tau omega. Okay? Keep it handy. Okay, that's all. I'm going to do a problem from the homework regarding the power, so I'll come back to it. It's a very simple concept. I'll come back to it. And the next topic is angular momentum. The problem with the program that I'm using as a screen reader, it does not allow me to create a video that is greater than 2 hours. That's just the nature of the subscription that I have. So I'm always, as I talk, I'm looking at the clock. Right now it's 1:30, so I need to be done with the video before it hits 2 hours. Otherwise I'm going to have to chop it off. So hopefully I'll be able to finish it. Okay, so the last topic is angular momentum. It is a little bit of a larger topic, so I hope I'll be able to finish it within half hour. Anyway, so I have angular momentum. So what is angular momentum? Well, it's analogous. The first thing I want to say about it, it is analogous to linear momentum. Remember linear momentum or momentum? Remember momentum? Momentum is equal to mv, right? And it's a vector quantity, so it is v, where v is a velocity. The rotational version of momentum is called angular momentum. It has the letter L, capital L, and it's equal to mvr. Okay, let's remove the vector, but it's mvr. R here being the radius of rotation, v is the velocity, and m, of course, is the mass. Okay, there is not much collision. We don't deal with collision regarding to angular momentum, but basically that's what angular momentum is. Let me explain it to you in terms of the Earth rotating about the sun. You may know that or not, I'm not sure, but the Earth goes around the sun in an elliptical path. It looks something like this. Again, this is a little bit exaggerated how it looks, but it looks like an elliptical path that looks something like that. Wow, perfect. Okay, I rarely get a perfect circle or ellipse. So, and according to Kepler's first law, the sun is located at one of the foci of the ellipse. If you don't know what that means, it doesn't matter. But basically, here is the sun. The sun is not located at the center. Okay? It's not located at the center of the ellipse. It's actually at one of the foci, focus, from the plural of the word focus. It's one of the foci of the ellipse right here. And you got the Earth goes around it like that. Here is the Earth, and it's going around it like that. Okay, that's the velocity of the Earth right here. Okay, so suppose, and this is the distance from the Earth to the sun. You see what I'm saying? I'm going to call it r for now. Okay, as you can see, this R is constantly changing. See that when the Earth is here, right here, the R is shortest, and when the Earth is here, the R is largest. You see that? So it really varies all the time, this distance. So what happened? How does that affect the Earth? Well, here is how it works. We have something called the conservation of angular momentum. Okay? What that means that the angular momentum at any position, say for the Earth around the Sun, at any position, have to be equal at all time. In other words, if the Earth is located, say, right here, let's call that location 1. And let's call that location number 2, okay? And the angular momentum at position 1 must equal to the angular momentum at position 2. It's equal to the angular momentum at position 3 and 4 and 5 and so on, okay? Angular momentum is conserved, which means angular momentum is always exactly the same all through the path of the trajectory. You understand what I'm saying? Okay. What are the consequences of that? Well, we know that angular momentum is equal to mvr. So let's just concentrate on position 1 and position 2, just for the sake of argument. Look at that. So the Earth here is moving with some velocity v1. And it is at a distance r1 away from the Sun. Here it's moving, remember, the Earth going in this fashion. So in this case here, the Earth is going with velocity v2, and it is what at a distance r2 away from it. See that? Well, if I am going to insist that L1 and L2 are equal, then mv1r1 must equal to mv2r2. Make sense? They have to be. You can ignore the math because they're going to cancel out. So basically v1r1 must be equal to v2r2. Are you seeing what's going on so far, or you haven't? All right, let's continue. So notice here at position 1 that R1 here is very small compared to R2. Okay? Where here R2 is very large compared to R1. Well, if the product R2 and V2 must equal to R1 and V1, what can we say about V1 and V2? What we can say is the following, is that if let's say the Earth is at position 2, so it has going with some velocity v2 with some large distance r2. When this large distance becomes small, what will happen to the velocity? It will become very large. Make sense? In other words, the Earth is very slow here, but very fast here. And in between, it's actually accelerating until it becomes fastest here. And then it decelerating, slowest here. And so on. You get that? So the Earth is constantly changing velocity as it goes around the Sun. Why? To keep because of the conservation of angular momentum, and to keep this product mvr the same. Okay? That's the essence of angular momentum, conservation of angular momentum. Another example that you are probably familiar with is the ice skater. Okay? So the ice skater, with her elegant dancing and movement on the ice board. So she has her arms outstretched, and then she sets herself spinning about the vertical axis, something somewhere around above her head. And then when she pulls her arms towards her body, towards her chest, if you will, she starts spinning much, much faster. Now, why is she spinning faster? Well, again, it is the conservation of angular momentum. Here is this ice skater. Let's say a top view. Here is her head. Here is her arms. That's the fingers here. Here is her. Those are her fingers. And then she's spinning. Remember, this is the distance R2, let's call it. Okay? And she's going with some velocity. We'll call it V2. Okay? Now, when she brings her arms around her body, around her side, for example, say here. See what I'm saying? I can't draw it. Okay, in this case, the radius of rotation is just r1, and then this is the velocity, v1. Well, in order for L1 to be L2, m v1 r1 equals to m v2 r2, the angular momentum, she starts spinning really fast here, okay, just because she brought her arm towards her body or to her sides. You see what I'm saying? That's the essence of conservation of angular momentum. Okay, so what is it equal to? Angular momentum, L, is equal, like I said, there are three versions for it. MVR, that's the first one. The other one is L equals to I omega. I omega. I here is the moment of inertia, of course. Omega is the angular velocity. And the other version, well, we know that P equals mv, the momentum. Well, notice that L equals to mvr, so L, you can say that is equal to PR, because mv here is P, okay? This relationship, you want to just keep it in mind. You may need it, you may not need it, but those are the two important ones, especially the second one here. Okay? All right. Let me do an example and show you how this works. I'm going to go to example 10.9 in the book. Let's go back to it. Page 299. 299. All right, you got this guy right here standing on a stool, and he has dumbbells, and then he's spinning around, okay? And then he brings the dumbbells towards his side or towards his chest, whatever. So he starts spinning faster, okay? Just like the skateboard dancer, the ice skater. What do you call it? Ice skater. Okay, so here it says in this example, let's see, a physics professor stands at the center of a turntable holding his arms extended horizontally with 5 kilogram dumbbell on each hand. There it is right here. He is set rotating about the vertical axis. The vertical axis is somewhere above his head like that. You see what I'm saying? Making 1 revolution in 2 seconds. So he gives you omega in a funny unit, but he gives you omega. 1 revolution in 2 seconds. His moment of inertia without the dumbbells is 3. Okay, 3 kilogram meters squared. When his arms are outstretched, and drops to 2.2 when his arms are pulled in close to his chest. Okay, I'll come back to all of that in a sec. Let me just finish reading. The dumbbells are 1 meter from the axis initially, so that means this is 1 meter right here. Okay, and then when the dumbbell is close to his chest, he's at 0.2 meter from it at the end. Okay, so this is 0.2 right here. Find the professor's new angular velocity, omega, if he pulls the dumbbells close to his chest, and compare the final total energy with the initial value. All right, let's see how we do this problem. Not a difficult problem, promise. Not like the latter problem. Then 9. Let me draw a picture of this thing. So we got Mr. Stickman here. There he is. Here is the stool, or whatever you call it, and thus his arms stretched out. There's the dumbbell right here, just like that. Here is the axis of rotation right here, like that, omega. We'll call that situation 1. And then the second situation, well, he is same. I'm going to draw the same picture. And so now his arms are here, the dumbbells. And then he's still rotating, but at a slower or faster? Should be faster, right? We'll call that omega 1. That's omega 2. And that's situation number 2. Okay, he says that the distance from here while his arms are stretched, I forgot what it is. I forgot. Let me go back. 1 meter. And then 0.2. Okay, so this is 1 meter right here. And then here, the distance is 0.2 meter. Got it? Okay. So the dumbbells are 5 kilogram dumbbells. In each hand. And then he says when his arms are outstretched, his omega 1 that is 1 revolution per 2 seconds. That's what he said, not me. Okay? And then also he says that, what else did he say? Yes, okay. So he's asking for what is omega 2. Okay? You can pause the video and think about it. Make sure you understand the problem. You may not know how to answer it, but that's okay. But make sure you understand what the question is asking for. All right, so I want to use, excuse me, I want to use angular momentum. So angular momentum says I1 omega 1 equals I2 omega 2. Okay? So what is I here? I here, or shall we say I1? I1 here is basically the moment of inertia of the professor, the body, professor, okay, plus the moment of inertia of the dumbbells. You can add them up together, okay? Now, for the professor, he tells you what it is. He says it's 3. He gives it to you. Look. He says, yeah, his moment of inertia without the dumbbells is 3 when his arms are outstretched like this in this situation. And when they are dropped, his moment of inertia is 2.2. Got it? Okay. What about the dumbbells? Well, the dumbbells is mr squared, if you remember. For any object, it's mr. If it's a point object, it's mr squared. The mass of the dumbbell times how far is it from the axis of rotation, which is r. So in this case, the mass of the dumbbell, we have 2 of them, so it's going to be 2 times the mass of each dumbbell is 5, times how far is it when it's outstretched, which is 1 squared, right? Here's 1 right here. So in this, each of them is m. So we have 2 of them, 1 and 2. There we go. Okay? So this for I1, this is going to be 3 plus 10, and that's equal to 13. What is mr squared? That's going to be kilogram meters squared. There we go. That's the moment of inertia when the professor's arms are outstretched. All right, let's get I2. Same concept. I for the professor plus I for the dumbbells. Okay? And so for the professor, he said it's 2.2. It's given to me. He gives it to me, right? It's 2.2. And then for the dumbbell, well, the dumbbell in this situation, so it's mr squared, but r this time is 0.2. Okay? So that's going to be mr squared. And there are 2 dumbbells, so that's 2. M, it's, what is that, 5 kilogram. R squared is 0.2 squared. Got it? And when I calculate that, let me calculate it. 2.2. I got 2.6 kilogram meters squared. There we go. Now the next step is I want to use conservation of angular momentum, which is I1 omega 1 equals I2 omega 2. He gives me omega 1, but in a funny unit, he said 1 rev per 2 seconds. Well, I want it radian per second. So take that 2 to the side. It becomes half a rev per second. We've done that before, and half, the rev is 2 pi, so that makes it radian per second. Okay? So that will be pi, the 2's cancel out, basically 3.14 radian per second. That's what omega 1 in the proper unit. All I need to do is just plug all of that in there. So in this case, I will have I1 omega 1 equals I2 omega 2. I1, I just got it right here, guys. 13, and I2 is 2.6. Just plug them in. So I have here 13. I1 is 3.14 right there. Equals I2 is right here. 2.6 omega 2, and you just solve. So therefore, simple problem. I hope it is simple problem. And you just work it out, and then when you work it out, you get I got 15.7 radian per second. Okay? Then he says, the last part, he said, what is the kinetic energy? Is that right? Let me go back. He says, compare the total and, compare the final kinetic with the initial one. All right, that's not difficult. You think you can do it yourself. The kinetic energy, because it's rotational, so it's 1/2 I1 omega squared. That's initial. And then the final one is IK2 equals 1/2 I2 omega squared, omega 1, omega 2 here. And then when you calculate that, you will get, I'm just going to get you the answer. So here we go. I think you did it. There we go. So 1/2 times 13 for I1 times omega 1 is 3.14. And you get 64. And then for K2, I'm calling it K2. He called it final. And you just plug it in and you get 320. Okay? So this will give you 64 joule. And this will give you 320 joule. Okay? And that's it. Okay, good. I think I am pretty much done with everything I wanted to cover. So let me do maybe a couple of examples from the book. Let me do number 19. This is homework. 10, 12, 19. If I have time, I'll do one more, but number 19, right there on page 314. Let's do it. 314. Number 19, right here. Level 1, it's not bad. Okay, it says a playground merry-go-round has a radius of 4.4 meters and a moment of inertia of 245 kilogram meters squared and turns with negligible friction about a vertical axis through its center. Okay, a child applies 25 Newton force tangentially to the edge of the merry-go-round for 20 seconds. All right. If the merry-go-round is initially at rest, what is the angular velocity after 20-second interval? All right, simple problem, I hope. B, how much work did the child do on the merry-go-round? And C, what is the average power supplied by the child? Okay, so basically what we have here is the, let's make it a top view. Here's the merry-go-round right here. That's the top view. And then the child is pulling with 25 Newton? 25, forgot, 25 Newton? Yes, 25 Newton. I'm looking at the book here. Like that. The radius of it is R equals to 4.4 meters. The moment of inertia of the merry-go-round is 24.5 kilogram meters squared. And then A, he says, the child applied, the child applied, he said the initial angular velocity is 0, right? The merry-go-round was at rest before the child pulled it. And for a time of 20 seconds, so after 20 seconds, what is the new omega? Well, that's just pure kinematics, isn't it? We can just use kinematics in this case. So omega equals omega naught plus alpha t, correct? I know t is right here, 20 seconds. Omega naught is 0, but we need alpha. How do we get alpha? He didn't give us alpha, did he? Well, here is where Newton's second law for rotation, tau equals I alpha, comes into the rescue. Tau equals I alpha, correct? I is given to us right here. I need alpha, but what is tau? Well, tau is equal to what? It's equal to RF. Remember? I alpha. And R and F are given. Here is F right here. This is F. And R is given to us as well. So therefore, alpha is RF over I. See what I'm saying? So go back to my kinematic equation. So omega is equal to, that's 0. So RF over I times T. There we go. Just plug it in. So R in this case will be 4.4 times F is equal to 25 divided by 24.5 times the time is 20, and then you'll work it out. You'll end up with 89.8 radian per second. There we go. Okay. B says how much work did the child do? Okay, well, we know that work is equal to what? Go back to my what we talked about just 20 minutes or so ago. We said work is equal to tau delta theta. All right, so all I need to do is to get theta. Again, I can use kinematics. So theta is equal to omega naught t plus 1/2 alpha t squared. I already got the alpha right here. I can get a number out of that. See what I'm saying? And then omega naught is 0. So in this case, theta is equal to 1/2, and alpha is this alpha. If you would calculate it, I'm sorry, I'm in a hurry because I'm looking at the clock. I got 8 minutes before 2 hours. So alpha here is 4.49 radian per second squared. You can work it out and make sure that I've done it correctly, and then you just work it out here. So it's going to be 4.49. T squared is 20 squared. Is that right? And then you calculate theta, and that will be 898 radians for theta. Okay. And then he wants the work. Well, work is tau theta, and tau is what? It's RF theta, and we have everything. So it's going to be 4.4 times the force is 25 times theta. I just got it, 898, and then the work in this case would be 9.88 times 10 to the 4th joule, right? And then C, the last part. He says, number 19, what is the average power delivered or supplied to by the child, or delivered to the merry-go-round? Well, the power, if you remember, is equal to work over time. See what I'm saying? And work is, I just got it. We just got the work right here, and we know what the time is. So it's a pretty simple problem. It's going to be 9.88 times 10 to the power of 4th divided by 20, and therefore the power delivered to the merry-go-round is equal to 4.94 times 10 to the 3rd power. Sorry, that's watt. Trying to erase that thing. There we go. Okay. I have a few minutes left. I think I'm going to stop here. Please let me know if you have any question on any of the problem. You can just post them under Ask the Professor, and I'll be more than happy to help you. Okay? Bye-bye.